When you first see exercise 3.2 in the art of electronics, it just looks like another maths problem, which seem to be very common in art of electronics. But it's actually one of the key steps in understanding what a FET really is. This little derivation links the gate voltage, the drain current, and the channel resistance, the three things that define how a FET behaves. It shows that the same device can act like a variable resistor, a clean amplifier, or a switch, all depending on where you bias it. By working through the square law relationship as asked in this question, today we are going through exercise 3.2 and we need to derive the preceding scaling law. The scaling law being the RDS is proportional to RG0 times VG0 minus VTH divided by VG minus VTH. I will talk through these terms in more detail later on in the video. By working through the square law relationship, you learn where transconductance and output resistance come from. They're just slopes on the same curve, and I think that's why this question is important and you should aim to understand it as well as you can. But before we answer this question, a quick thanks to PCBWay for sponsoring this video. If you're designing your own boards, PCBWay makes it stupidly easy to get professional results. You just upload your Go files, pick your options, and they handle the rest. The quality is rock solid, turnaround times are fast, and you can even order assembled boards if you don't feel like soldering 100 SMD parts yourself. So whether you're building a FET test jig or a full-blown audio board, PCBWay is the place to get it made. You can check them out using the link in my description below. It helps support the channel and keeps these projects going. So the equation we need to derive is RDS equals RG0 VG0 minus VTH divided by VG minus VTH. So first, I'm going to start with some things that we should know for answering this question. And the first one is basically this equation, which is the drain current, and it is equal to a value K, and in brackets you got VGS minus VTH squared. And this is given to you on page 147. And the book also says from there, you can derive the transconductance, GM, which is equal to ID VGS, and that's delta ID delta VGS. So that's VGS from there and ID from there. So basically you're just taking a derivative of this equation to get to transconductance. Now, before we go too much further into the question, I think it's good to understand what all of these terms mean. So ID is the drain current, and that's basically a current that's flowing from this side up. I mean, the direction doesn't matter really. IDSS, which is a term that we haven't got to yet, but IDSS is drain current at zero gate bias. So basically the maximum current through the device when the gate source voltage, which is this voltage over here, is equal to 0. VGS, which is this one here, is the gate source voltage. So obviously you have your FET, you have source, drain, and you have a gate. And VGS is this voltage. This voltage controls how much the channel will conduct. So basically how much current you're letting through. GM is the transconductance. VTH is the threshold voltage. I think threshold is used more for MOSFETs, and it might be VP for JFETs. So that's basically the gate voltage where the channel cuts off. So there's no current allowed to flow except for the small leakage current. And RDS, which is this one over here, and the main part of the equation that we're deriving, is small signal drain source resistance. So that's basically the incremental resistance seen looking into the drain for small AC signals. The last thing, which is this constant that I briefly mentioned, is basically the device constant. It kind of tells you how strongly the transistor responds to gate voltage, as you can see from this side over here. And you got the square law over here, which is implied in the question. A bigger K means the device can produce more drain current for the same gate source voltage. I think the K is dependent on like physical parameters, And this value is typically not listed in datasheets, as far as I know. So this equation obviously becomes a little bit harder to kind of work with, whereas this equation doesn't have k, and it's probably one of the reasons why we're deriving it as well. Okay, so let's start with this equation over here, which is on page 147. And what we're going to do is basically go through the differential and then try and get to this equation for the question. ID is equal to K VGS minus VTH squared. We know that GM is equal to delta ID delta VGS. So if you do the differential on this, you basically get 2K VGS minus VTH divided by 1, but whatever. So this is one of the equations that we'll need to remember. In the question, we are also told that RDS is equal to 1 over GM. And you can see this relationship from the channel model, that the channel resistance in the linear or the low VDS region is inverse of the transconductance. So what we're going to do is substitute out the GM for this equation. So we get RDS is equal to 1 over 2K VGS minus VTH. Now, if you know the resistance of RDS at some reference gate voltage, let's say VG0, then we can calculate RG0, which is the RDS at the known reference voltage. We can rewrite this equation as RG0 is equal to 1 over 2K VGS VG0 minus VTH. Now what we need to do is basically rearrange these two equations to get 2K on the outside or on the left-hand side by itself. Once we've done that, we can basically put the two equations together. So I'm going to show you for one of them, but not for both. So let's do RG0, and the other one is pretty much the same. So 2K is equal to 1 over RG0 VG0 minus VTH, and all I've done is basically times both sides by 2K and then divide both sides by RG0. So obviously you end up with RG0 on this side and you end up with 2K on this side. And then you can write the same thing for the other one, which is 2K, and in this case it will be RDS VGS minus VTH, and we get 2K on this side as well because they're essentially the same equations. Now if you create these two together, we end up with 1 over RG0 VG0 minus VTH is equal to 1 over RDS VGS minus VTH. Now the equation we need to derive has RDS on the left hand side. So what I'm going to do is basically multiply both sides by RDS first. So then RDS disappears from here and appears over here. So let's do that. VGS VTH, and we get RDS over here. And then what I'm going to do is multiply both sides by this part. So we end up with RDS is equal to RG0 VG0 VTH minus VTH over VGS minus VTH. It's gone a little bit messy here, so let me just fix that. So you can see we've got to the equation that is basically required on the question, and we've used some of the things that were given to us in the book a little bit earlier on in the chapter. And this is the solution for this question. So hopefully you've learned something from this tutorial. Make sure to check out my other videos on electronic projects and become a channel member to support the channel for more projects like this in the future. Thank you for watching. Bye for now.